Welcome back. In this video, we're going to continue the chapter on the electronic structure of molecules, and we're going to build on the work from the beginning of the chapter where we looked at solutions to the Schrodinger wave equation for molecular hydrogen cation. In that problem, we had a single electron, and it was orbiting around two nuclei, protons in this case, and those nuclei were positioned at the foci of a ellipsoidal coordinate system. By using that coordinate system, we were able to come up with an exact solution to the Schrodinger wave equation, and we could get the eigenfunctions and the eigenvalues, the energy of that wave function, and found that it actually matched perfectly with the experimental measured values for the molecular hydrogen cation energy. Now, in the process of doing that exact solution, it suggested to us an approximate approach that we call a linear combination of atomic orbitals approach, where we bring two atoms together and we use the atomic orbitals on those atoms as they come together to form a molecular orbital. And there can be constructive and destructive interference, and we can build this molecular orbital from this combination of atomic orbitals using a variational theorem approach with adjustable parameters to get to a minimum energy to get us the best possible guess or approximation for the ground state wave function for that molecular orbital. So what we're going to do now is we're going to build on that idea, which we examined for the molecular hydrogen cation. We're going to take this linear combination of atomic orbitals approach, and we're going to try to apply it to multi-electron molecules. And of course, that's a much bigger task, because now instead of one electron, we're going to have n electrons. And in the Hamiltonian, which I've written here in atomic units, this is the kinetic energy term for those n electrons. We're also going to have m nuclei that are in this molecule. So we're going to have an attraction force of those electrons, n electrons, to those m nuclei, and that's going to be this term 2. There will also be a repulsion between the electrons. That's something we didn't have in the molecular hydrogen cation, and that's going to be contained in this term. And there will also be a kinetic energy term for the nuclei, just like before with the molecular hydrogen cation. And then there'll also be a coulombic repulsion between the nuclei too. Now, this Hamiltonian, which I've written in atomic units, ignores the spin-orbit coupling and relativistic effects, which you could add on, but we're just trying to do this as simple as possible, which is already quite complicated here, to get a understanding of how these approximate solutions can work. Now, one of the solutions we learned at the beginning of this chapter was the Born-Oppenheimer approximation, and that allowed us to split the molecule's wave function into an electronic part and then a part that's associated with the motion of the nuclei, which holds the translational, rotational, and vibrational motion of the nuclei is all described by that wave function. So what we're going to do is we're going to focus on this electronic part, and this other part here, which has the translation, rotation, and vibration, we've pretty much solved that already in the earlier chapters in the class. So we're just going to focus here on this solutions for the electronic part of the molecular wave function, knowing that we can actually write the total wave function as this product. Now, the electronic wave function then is going to be obtained by solving this wave equation here, where now we have just the electronic Hamiltonian, where it's moving in a field of m fixed nuclear charges, and so they're not moving, and we're going to construct our wave function using the orbital approximation, where we'll use these Slater determinants to make sure we create antisymmetric combinations that satisfy the Pauli exclusion principle, and this will be then used as we try to solve this problem. Now, this is the more general approach, where we're just going to look at this simple MO picture from a linear combination of atomic orbitals. So if we take just a simple picture like the H2 molecule, so now we have 2 electrons and 2 nuclei, we're going to write down the Slater determinant, and we expand it out in this form here. And now we have, here is the spatial part, and here is the spin part. So this is the electron spin part, which we have to write in this way in order to make sure that our wave function is antisymmetric with respect to electron exchange. Now, if I focus in on this spatial part, and I know these are the these are the molecular orbitals, and I'm going to write those molecular orbitals as linear combinations of atomic orbitals. So right now I'm going to take then the 1s orbital on nucleus A and the 1s orbital on nucleus B, and I'm going to write that linear combination to be the molecular orbital for this electron. And then I'm going to do the same thing for the other electron, the atomic orbital on A and the atomic orbital on B for the second electron. And that product there will be this spatial molecular orbital, spatial part of the molecular orbital. And if I expand that out, then you can see this expands out into 4 terms. And these 2 terms here are with electron 1 in the 1s A orbital, and electron 2 is in the 1s B orbital. And over here we have electron 1 in the 1s B and electron 2 in the 1s A. And these are the electrons sort of uniformly distributed in the molecule. In addition to those, though, when we do this expansion, we also get a case where we have electron 1 in the 1sa on nucleus A and electron 2 in the 1sa. So in other words, both electrons are on nucleus A, and there's no electrons on nucleus B in this particular term here. In this term, we have the opposite. We have electron 1 on the B nucleus in the 1s orbital, and electron 2 on the B nucleus in the 1s orbital. And so here we have both electrons on the B and no electrons on the A atom. And so this and this, these 2 cases here are kind of like these kind of cation and anion pair, whereas these guys over here, these 2 terms are with the electrons sort of more uniformly spread out across the molecule. Now, these actually probably don't make that much sense. We don't really imagine that the molecule, the hydrogen molecule, is going to have all the charge over to one side. So one of the problems of this linear combination of atomic orbitals approach, this MO theory approach, is that it creates these terms here which are probably overemphasized. They don't really occur that often. I mean, there is a probability that the electrons will go both to one side or the other, but the probability of that is going to be much smaller than what this term is actually indicating here. So this approach then does have some terms that we need to sort of adjust to correct. One way that people do that is using an approach called valence bond. And the idea is just simply to just throw those terms away because they don't seem realistic. And then that's what's done here, where we just get rid of those terms and we just keep these 2 terms here. And this is what's called a valence bond approach, and we still need our spin part here to keep the wave function antisymmetric. And this makes sense for hydrogen, but on the other hand, if we were looking at HF, or carbon monoxide, where we have maybe a situation where we expect the electrons to spend more time on one side and the other side, then we might want to include these terms where the electrons have a higher probability to be on one side than the other. So we want to have actually then, and we're going to develop this approach, is some kind of approach that maybe takes an intermediate ground between here, where we include these terms, but we also include these ionic terms here with perhaps some coefficient here, some kind of parameter that we can use in some kind of variational approach. All right. Okay, so we're going to stop here, and in the next video, we'll look at molecular orbital diagrams and electron configurations.